So tonight is the first lecture in a three-part series on sea level rise. So we have tonight a leading scientist, whom I will introduce in just a minute, who's going to talk about sea level rise from a global perspective. Tomorrow night, in this same auditorium at 7 o'clock, we will have an historian, John Gillis, who will talk about sea level rise from a personal perspective throughout history and looking into the future. And then next Wednesday, we will have another scientist from the Scripps Institution of Oceanography who will provide a California focus. If you can come to all three, I think you would have a really, really good overview introduction to the topic of sea level rise, what causes it, how it gets manifested, and what the challenges are in the future, and the choices that people have to adapt to this. And also to mitigate to the extent that's possible. Now, this is a picture. This is French Parliament, and they're having a debate as to whether sea level rise is real or not. When they started the debate, they were standing on solid ground. Well, it's actually in Sacramento, but I shouldn't say that because where we're located. All right, let's get that off before I get into any more trouble. Tonight, we're going to hear from Dan Cayan. Dan Cayan is one of the world's great experts on sea level rise and on climate change and how it impacts California. This is a very important National Academy report that came out, 2 years ago, was it, Dan? 2012. Sea level rise for the coasts of California, Oregon, and Washington. And if you go to the National Academy, all of their publications are overpriced, but you can download a free PDF, and this is one that's really worth reading. And even if you just read the part in California or in Southern California. Dan is a research meteorologist with the Scripps Institution of Oceanography at the University of California, San Diego. He's also a researcher with the U.S. Geological Survey, and he is the head of the California Nevada Applications Program. It's a RISA team, which is a regional team dealing with climate change. They play a lead role in California climate change vulnerability and adaptation assessments. He earned his bachelor's degree in meteorology and oceanography at the University of Michigan in Ann Arbor, and his PhD in oceanography from the University of California, San Diego. He's been at Scripps since 1977, and he's been of enormous help here at the Aquarium when we had the public launch of the photographic exhibit that's out in the Great Hall and upstairs called Sink or Swim that came to us from the Annenberg Space for Photography. We had the launch event, and Dan was our on-camera expert, and it was captured by a number of television stations. He's also been helping us with the project that we're doing for the mayor of Long Beach, who wants Long Beach to become a model of a climate resilient city. And among the things you have to deal with are in climate change, you have to deal with sea level rise and coastal flooding. And both Dan and our speaker next Wednesday, Ron Flick, have been very helpful to us. So he's a good colleague, a good friend, and an outstanding scientist. Please join me in welcoming Dan Cayan.
Am I coming through? Okay, good, thanks. Well, what a resource you have here. You know that, but anyway, I'll say it anyway. I'm gonna try to give you a survey of sea level rise from a pretty large scale perspective, and then we'll sort of zoom in towards California, but as Jerry mentioned, in a week you'll hear from my colleague Reinhard Flick, who's going to talk about impacts along the California coast of sea level rise. He's a really good speaker. He works for the California Department of Boating and Waterways, as well as having an appointment at Scripps. So when we talk about sea level, I think it's okay if I wander around. Okay, it's useful to get an idea of the water on the planet Earth, because really, when we're talking about sea level rise, we're talking about the movement of water from one component of the total water pie to another. And when you look at the water on Earth, this is what it looks like in comparison to the globe, if we put it all into a sphere. So the globe turns out to be about 8,000 miles in diameter. That's Earth, and this water sphere is about 860 miles across. If you took all the water in the various compartments on Earth and condensed it, this little sphere here is the land liquid water, and then this is the water that is in lakes and streams. So you can kind of get a little bit of a perspective of what the water, we do have a water planet, but when you see it in this view, it looks like water is really a pretty thin skin, which it actually is. And of course, we are relatively short compared to the dimension of the globe. So in many cases, water stocks look pretty robust to us. But anyway, this to me was a really interesting way of getting a perspective on the water components. So as I say, we are a water planet. The great Pacific Ocean basin. 97 almost % of the water in the global system resides in the oceans, and actually comparatively, if you convert the amount of water into a volume, that turns out to be 321 million cubic miles of water that is resident in the ocean. In comparison, there's 11 million cubic miles of water that is in various land stocks. And if we took 2 feet of sea level rise from glaciers and ice sheets, we would add this many 52,000 cubic miles of water to the oceans, or an increase in the hundreds of percent to the ocean body. So we're talking, what we're talking about with sea level rise is actually pretty incremental when you look at the totals. But it's greatly consequential. And, it's also consequential when you start subtracting from the water that we have on land. By the way, I think this number is wrong, so I'm going to have to do my homework there and correct that. I don't believe that there's an order of magnitude problem there. So just think of oceans really big, land not very big, and the amount of sea level that we're talking about is extremely incremental when you view it from this total budget perspective. So it turns out that ice on Earth is an interesting part of this problem, because what we're doing as climate warms is converting land-grounded ice into liquid water, and of course that's adding to the volume of water that we have in the oceans. So presently, about 10% of land area is covered with ice on Earth. Okay, now just to put that into perspective, during the last glacial maximum, that fraction actually reached almost a third of the land area on Earth was actually covered with ice. So the system is very dynamic. When you look at it in a long-term kind of geological timescale, but of course in recent times we think of the system as being rather stable, and what we're seeing now, of course, is a period that is actually not so stable. Glaciers, these ice bodies, store well over 50% of the freshwater land in the land system, and we've kind of, as you know, we've had periods of lots of ice and not so little ice. As recently as the 17th to the 19th century, we went through a little ice age where some of the glaciers actually grew and expanded in their coverage. But in recent times, actually glaciers globally have been declining and shrinking. There are glaciers in the United States, a lot of them, most of them in Alaska, but as many of you know, we actually have glaciers in, sorry, I'm gonna skip forward. We have glaciers in California. This is kind of fuzzy. This is the Dana Glacier in the Yosemite area back in the late 1800s here on the left, and near presently 2004 in a repeat photograph by Hassan Basajic showing how this glacier, like many in our western setting, have declined remarkably as time has gone on. Okay, so, whoops. I think I did something bad here. Let's see, there we go. Thank you. Thank you, team. This gives you an idea. We're talking about sea level, and we are here today, and this is looking at sea level from a long-term perspective. So this is going in the hundreds of millions of years before present. And as you can see, sea level has gone down markedly as well as gone up markedly in the past. And of course, periods where sea level has gone down are cold periods on Earth because we're harboring a lot of that water in the glaciations, the land ice, and then other periods where the Earth is much warmer. You can see that here. Unfortunately, the time scale here goes to present to the right, and this is going to present to the left. But as you can see, this is a measure of temperature on Earth, relatively stable recently, but you can see these very the thermal warm periods in the past that correspond to these epochs of very high sea levels here. So it's not unusual for sea level to vary, but it is unusual for sea level to vary in a very rapid fashion, and that's what we're starting to see in the present. Just to give you an idea of the march towards modern sea level here from the last glaciation, here's a series of proxy measures of sea level that have been taken by paleoclimatologists around the world. So you can choose your favorite vacation spot here, where they've sampled cores and geological formations and made a reckoning of where ocean levels stood in the past. And you can see that there's a pretty good consensus. There is variation, but it's actually, to my eye, this is stunningly coherent to look at this trace of how sea level in the last glaciation was as low as 120 meters below present-day sea level. And as then Earth warmed, in coming out of the glaciation, sea level rises. We've had a period now of 6,000 or more years where sea levels have been globally relatively stable. And during that period, and I think you're going to have a speaker that will talk to this tomorrow, Gillis, will talk about how a lot of civilization is founded and was able to establish during these periods of optimal conditions where not only climate but sea level was relatively steady. So we have a problem, and the problem is that our atmosphere is changing, and the reason the atmosphere is changing is us. We are loading the atmosphere with greenhouse gases. Greenhouse gases are gases that are not transparent to terrestrial infrared radiation. The way the planet energy balance operates is that we get shortwave radiation largely from the sun, solar radiation, and the planet has equilibrated, and what comes in as solar radiation then eventually exits the system in the infrared bands, and that's over this period that we just looked at, that's been balanced. These gases that are loading the atmosphere, carbon dioxide, methane, nitrous oxide, the fluorocarbons, are not transparent to that terrestrial radiation. So what happens is they absorb, they re-radiate to the Earth's surface, and then the planet has to warm to compensate. And that's what we're seeing. Right now, the globe is out of radiative balance because of these greenhouse gases. These greenhouse gases, several of them have long lifetimes, carbon dioxide more than 100 years. So the problem that we're producing today is a problem that the next generation and the next generation and the next generation is going to have to contend with. All of these have carbon dioxide, probably the most important of the human-caused greenhouse gases, has increased by 40% since pre-industrial times. We know that because we can harvest carbon dioxide in ice cores, and so we can look at essentially the ancient atmosphere from sampling air bubbles that are captured in ice. Okay, so this is just a schematic of this global energy system. The solar part of the input coming in, the terrestrial part going out. Clouds play a big role in this system, and that makes it complicated. Things like aerosols, we burn coal and other gases that makes sulfates. They get introduced in the atmosphere. That turns out to be a coolant globally because it reflects radiation. But because we're inserting so many greenhouse gases in the atmosphere, the net balance is actually estimated now at a little more than 1/2 of a watt per square meter going in more than is going out. 1/2 a watt doesn't sound like very much. These lights here are, I don't know, 70 watts or something like that. But this is 1/2 a watt per square meter over every square meter of the globe, 24/7. Okay, so it has this cumulative effect, and this imbalance is projected to grow. If we're lucky, by the end of the century, this will grow only to 3 or 4 watts per square meter out of balance. But if we're unlucky, the projections are for greater than 8 watts per square meter out of balance as this greenhouse gas repository continues to accumulate. Where's the heat going? So the heat is coming into the system, and the system is absorbing more than it has in the past. Well, people have chased this down. We know that the lion's share of the excess heating is going into the oceans. It's not just at the skin, at the surface of the ocean. It's now detected below 1,000 meters in the oceans, in all of the ocean basins. So all of the ocean basins are warming, at least subtly, and this warming will continue, and the warming that's taking place in the oceans is one reason why we have such a large inertia in that system, because it takes a long time to distribute that heat and actually get it expressed as a equilibrium temperature. It keeps warming and warming and warming. And that's why we like to say that we have a long commitment in the system, not only because the greenhouse gases are resident in the atmosphere for such a long time, but because we have these big thermal reservoirs in the earth by way of largely the ocean bodies. You can see that the land system, by comparison, is not nearly as strongly heated, or in terms of the amount of heat that it contains, as the oceans. So this is a figure that may be familiar. This is historical temperature, this going back 1,000 years or so before present, and we know what these pre-instrumental temperatures are because we've used various proxy measures like trees, like sediments, like corals that are recorders. They're essentially natural thermometers, and those have been translated with a lot of work by scientists in order to understand what their expressions mean in terms of past temperatures. And you can see that to large measure, this varies from a degree Celsius negative to, in this case, 1/2 degree Celsius positive, and you can see the envelope's rather broad, but basically relatively stable for several centuries here up to the age of industrialization. And the very tip of this got cut off, and that will come through in a minute, but the last century has seen a remarkable uptick in global temperatures. These are measured not only over land, but over the ocean basins. Here's the end of that picture. And then this is what is being projected by climate models in the next 100 years. These lower parts of these traces are the relatively friendly scenarios where greenhouse gas emissions, the continuing accumulation, is on the lower end, but these higher end scenarios are one that you might call greenhouse gas business as usual and fossil fuel heavy economies. Of course, no one knows exactly what trajectory we're going to take, and there's a big, not only regional, national, but international debate about that. And of course, technology may play a role here, but it's pretty clear because of our investment in a fossil fuel economy today that we're not going to change this in, say, the next decade. So we are probably committed to ride on one of these trajectories in the future. And you might say, well, 1.5 degrees, 2 degrees Celsius doesn't sound like too much warming. But again, this is a global number. This is a 24/7 number. To give you an idea of how I calibrate that, for every degree Celsius of warming in California in the winter and springtime, we lose about 1/4 of the present day snowpack. So with a 2 degree Celsius warming in the state of California, the Sierra snowpack in the springtime would have about 50% of what we've seen historically. And the 2 degree Celsius number is kind of the mid-range number when you look at these projections. So there's possibilities that the consequences could be a lot more severe than that. And of course, any system, virtually any system that you look at, is going to be influenced by this amount, this degree of warming. Well, back to sea level rise. This is what sea level rise is made out to be over the globe. So think of this average picture, and there's a number of measurements that go into this. That's the spaghetti that lives behind it. But what you see from this picture is that in 100 years, we've seen something like 17 centimeters of sea level rise. That's something like 7, 8 inches of sea level rise in a century. And these last couple of decades, which now, instead of having to resort to individual tide gauges around the world ocean coastlines and islands, which was used to construct most of this picture, we now have satellites that use altimetric measurements. They use radars in order to understand the distance from the satellite to the surface, and they are able to triangulate this and do this very accurately to millimeters of accuracy. And over this most recent period of about 18 years now, it turns out that sea level rise has increased in its rate from about 2 millimeters per year over this longer period to now about 3 millimeters per year over this last couple of decades. Why is sea level rising? Well, there's a number of effects. Part of them, if you live on a coastline, part of the reason sea level changes is because of geologic processes which raise the land or lower it relative to the ocean. But over this global scale, the two primary reasons why sea level is rising is because the ocean is is getting warmer and it's expanding thermally. It's a fluid. It's not incompressible. So like air, when you warm it up, it wants to expand. And the other reason that is becoming increasingly important is that we're melting ice, as we mentioned earlier. Ice in various forms. Mountain glaciers, the relatively small stocks of ice that live in higher elevation settings around the Earth, are largely declining. And we have two massive ice sheets, Antarctica and Greenland, that are also losing mass and contributing more water to the ocean basins. So a recent take on how much of each of those two processes makes it to be about a quarter that is associated with thermal expansion. So that's the contribution, because the ocean basins are generally warming up. And 3/4, however, are because of ice melt, because of the smaller glaciers, and the larger ice sheets are starting to dominate this balance, and in the future will continue, and actually will probably, this ratio will become disproportionately taken up by the ice mass contributions. You saw that one. I want to now turn to a report that was mentioned by Jerry in his introduction, that was the effort from the National Research Council that took up the problem of sea level rise along the coast of our western states here. This was largely instigated through the Department of Water Resources, the state of California, but it was joined in by the environmental agencies in Oregon and Washington as well. This was chaired by Tony Dalrymple and roughly 14 other members on the committee. I was actually one of them. And it considered the problem of what we might expect along these coastlines in the next century, taking aim at 2030, 2050, and 2100 as the sort of index points as we looked forward. Well, here's a picture you already saw, a picture of observed sea level rise in the past. This is just one more look at this. This is in millimeters now, so this is that sort of 17 centimeter kind of number that I mentioned a minute ago. And this is what, at least grossly, what sea level looked like before that, relatively unchanging, starting to rise, I guess, a little uncomfortably more strongly in these last couple of decades. So again, since 1993, when collectively satellite information became available, we've seen sea level rise rates increase to about 3 millimeters per year, which again, that doesn't sound like very much, but it's cumulative and it's increasing. And this is sort of an envelope of futures that could happen. As you know, as you're surmising, there's a lot of uncertainty, but there aren't any of these that go down. And the there's quite a range of possibilities, some of which get to be well above 1 meter of rise from the index point is right here. Well, I take that back. In this case, the index point is prehistoric, but the amount of rise since the year 2000 is over a meter when you make this out. So this could be a huge challenge. Even these low-end amounts are eclipsing the amount of the rate of sea level rise that we've seen historically. That 7 or 8 inches per 100 years could easily double. If we're unlucky, it's 4 to 5 times what we've seen historically. So the summary of what the committee, the NRC committee, concluded as far as sea level rise for 2030, and in this case, we'll be interested mostly in the California part of this. That's the orange shaded part, 2030, 2050, 2100. This dot here is what you can think of as the central estimate. So by 2030, we're seeing a number that looks pretty much like the amount of rise that we saw in the last century. So in 20 or 30 years, we're seeing as much rise as it took 100 years to achieve in the 20th century. By 2050, this number is up to something in the neighborhood of a third of a meter, or that would be a little more than a foot. So that's about double what we actually, a little more than about double what we saw in a century. And then by the end of the century, we're seeing almost a meter. Think of this as 3 feet by 2100. That would be 5 to 6 times what we saw historically. Again, there's the uncertainty is great, and it grows as time goes on because the amount of understanding we have in looking to the future is becoming greater. You remember Yogi Berra said prediction is easiest when you're looking backwards rather than looking forwards. So, but the higher end possibilities here are getting to be really uncomfortable, and that's the kind of thing where if you're a decision maker, you have to weigh the consequences and the costs in determining how you're going to grapple with and contend with the risk. So this is to some extent, it's a probabilistic problem, and it's one that you weigh depending on your exposure and your resources. The other thing that we need to point out is that sea level rise is not a monolithic rate that exists in the same fashion throughout the ocean basins. So this goes back to the beginning of the satellite era, 1993, and this is the amount of change that we've seen in that period, which 93 to present is a little over 20 years. And what you can see is that these reddest areas here are starting to flirt with about 20 centimeters of rise. That's not what's happened along the California coast. In fact, the California coast, since the the mid-90s hasn't really changed that much. The Western Pacific, however, we're seeing numbers that are much greater than 10 centimeters. They're much greater than the global average over this period, which 3 millimeters times 20 years would be 60 millimeters, which would be 6 centimeters. So the average of all this should be sort of in the pale yellow area. But we see that parts of the Pacific have had, and Indian Ocean have had a great amount of rise. Other parts, very little. In fact, some areas have actually declined. We think this pattern of sea level rise is owing to the wind circulation over the Pacific, and we think the wind circulation changes over timescales of 10, 20 years, and we don't think that the wind circulation along the eastern boundary of the Pacific is, for decades and decades, going to be able to circumvent sea level rise. We think that eventually this is going to reverse. So this, we think, is a natural climate fluctuation, and we think that this picture will probably look different if we were to meet again in 10 or 20 years. We would probably see something that's not of the same arrangement. Well, the other thing along our coast, and you'll get more of this story when Reinhard Flick comes and talks in a week, but our sea level problems in the short term are not going to be created because of these relatively slow incremental rises. They are going to be felt when those rises are coupled with extreme events. And our extreme events, in general, along the West Coast are not Hurricane Katrina type of events. They are winter storm events, such as this scene from January of 1983, where we had a very large El Nino. We had massive cyclones, winter storm systems that were spawned off the coast of Japan. Took a few days to cross the Pacific Basin, and they not only had low pressure, which rises sea level, but also carried with them big waves, which cause a lot of coastal issues. In that winter, in January and March of 1983, we lost a lot of the vulnerable structures along this coastline, including the pier at Scripps, which was damaged that year, and it was rebuilt in the next year or so. Here's a reckoning of the big events that we've had in sea level along our coast using the lens of the San Francisco tide gauge going back to just after World War II. This is that 1983 year, and this is another large El Nino, 1997-98. Those 2 years really stand out as the years that produced the largest sea level anomalies, the big extremes. This is the number of hours of exceedance. The average for this, if every year was the same, would be down here. But you can see that some years really have no problems whatsoever. And in the 2000s, we've had sort of mediocre numbers of sea level extremes. But occasionally, we get these big winters. And those are the times where we really have to be on guard and vigilant. Picture of the large storms that happened. This is predicted sea level, this blue curve. This is observed sea level. These red crosses in January of 1983. This again is San Francisco. And in many locations along the California coast, 27 January of 1983 on a very large tide was the highest sea level in the instrumental record along the coast. That record stands today in many cases. As time goes on, when we look at these projections of sea level, and then we layer onto it a model that represents weather and climate, and we essentially simulate hourly sea levels, and we count the number of hours where we have an exceedance. So think of the exceedance as something that would exceed a seawall at the rate of maybe one time every year. And so the number, historically, you would get an average of about 1. Well, in this case, I have it in feet. But this is the number of hours, and I guess that number would be 1 hour out of every year. But by mid-century, you notice the number of hours of exceedance is climbing to hundreds, and then by end of century, it's climbing to thousands. It's not because we're getting stormier, it's because the ambient level, the bathtub, is filling up. So we're getting more and more chances where we get overtopping, inundation, flooding, and so forth. That's what's going on with sea level rise. So to conclude, in California, sea levels are anticipated to rise over the next century. There's quite a wide envelope of possibilities, but a sort of round number that the community is looking at these days is about 1 meter of rise, 3 feet over present-day levels by the end of the century. That's the kind of number we're looking at globally. And remember, globally, sea level is rising because the oceans are warming, because the planet is warming, because the ice is melting, and it's adding to the ocean volume. Here along our coast, we'll probably have the greatest problems when we have high tides and we happen to have a large storm at the same time. Oftentimes, those odds of that large storm impact is heightened when we have large El Niños, which activate the North Pacific storm track. Wetlands, this was a result of this report. In some cases, we can use our natural settings as buffers to sea level problems because wetlands tend to grow up as sea level rises. In many cases, however, we've actually we've managed the system so wetlands are not part of the picture anymore. So this may not be appropriate to many of the urban settings that exist in California. A wild card along our coast, which I did not talk about, but when you look at the geologic record, there's evidence for really massive earthquake caused changes in our geologic profile, where we get the coast actually sinks, so we get a lot of inundation. Such as was observed in Japan and Chile in recent years or decades. And if you look at the geologic record, that's happened repeatedly, but at a time scale of every 500 years or so. But it's something that we we should be aware of along this coast. There is a lot of uncertainty in these projections of sea level for a number of reasons, part of which we don't completely understand the climate system. The ice part of the climate system is not well handled. It's in many cases not represented in global climate models, so there's a lot of offline calculations that go on. Hasn't been observed very well. That's being addressed, but in a piecemeal fashion. And I guess in short, this is a developing science, so it's one in which the answers hopefully will become clearer as we move on into the future. As far as the projections, we probably have more certainty as to what's going to happen in the near term than in the far term. So by 2100, there's so many things that could occur that the envelope of changes becomes quite broad. So thank you very much, and I'll turn it over to Jerry.